for the past couple of months and that I've just kind of started to wrap up recently. 30 Cycles Roots Free. Pretty funny name, I think, and I guess you'll get it at the end. But we're going to be talking about formally timing binary code, so giving some kind of time bound for how long some code takes to run. So just a little bit of background. I work with Kevin Hamlin and Christoph Hauser. Hamlin is a professor here at UTD, and we study formal verification, which is the idea that instead of relying on unit testing for critical code, you instead write a mathematical proof that it does what you want it to every single time for all possible inputs. And that way you just get a better assurance that your plane isn't going to blow up because someone forgot to, someone had an off by one error. That would suck real bad, right? And we also specialize in binary code, which enters a lot of really cool implications that you normally don't think about on the high level area. So we're constantly thinking about whether or not our memory buffers are overlapping, or how when you're doing modular arithmetic that the number could overflow or underflow, or the idea of like a function call being not really a thing at the binary level. It's all just jumps. And so those really enhance the experience and make it harder, but also extremely interesting. And so we're often writing proofs that show a function is correct. So we have some idea of what it means for this function to return the right thing. But our verification system has actually turned out to be flexible enough to prove basically arbitrary properties about code in any kind of form you could think of. So what's the problem, at least in this talk? So I was hired at Dartmouth for the summer, and the problem statement that I knew about was, let's say you have some binary code, and it's got some kind of timing constraints. So this is binary code that's running in an airplane, or it's running in a nuclear reactor, and if it takes too long to do something, something blows up and kills people, and that's bad, right? Let's say that you take that code and you patch it somehow. Maybe you want to add control flow integrity, so you basically put a bunch of checks around all of the jumps in the code to make sure that it's jumping the right places. Well, the CFI works, and that's great, but you've just added a bunch of code, so what if you broke the timing constraint? And so the question we want to ask is, how can we ensure that patching doesn't break the timing constraints? And we debated how to tackle this problem for many months until we started to narrow down the problem, and we settled on the idea that we already just don't know how long code takes to run. Not really. We have these loose ideas of complexity, right? We all have studied or will study big O notation, but no one can actually write a formal proof that some function takes n cycles, n clock cycles to execute from start to finish for some given inputs. That's not a capability that we have yet. And that means that your nuclear reactor controllers and all of your sensitive things that have real-time properties, they're basically running on fairy dust and hearsay and conjecture to make sure that nothing is blowing up because it took too long. And I don't know about you, but that is scary and not what we want to happen, right? And so if we did have these proofs, it would be so useful to have perfect knowledge about how long something takes to run. And so, all the way down to the kernel level, there's this thing called FreeRTOS that we'll talk about later. It'd be great to have timing guarantees about that. Or the user level stuff, such as autopilot, or the reactor code, or all this stuff that people are building on top of real-time operating systems. It would be great to have proofs about those. And a cool one that I've been trying to push more is constant time cryptography. So we'll also talk about that a little later. But there's immediately a solution in mind if you already study formal verification. Step one is to build some formal models of software and CPUs. So you need some description of exactly what a CPU does under this instructions, guidance and whatnot. And then you need to formally state your timing constraints somehow. You need to relate a number of clock cycles to a program. You need to write the proof that the code actually meets the timing constraints. And then you want a machine to check that your proof is correct. Because if I write a proof but nobody looks at it and nobody verifies that the proof is right, well then what was the point of writing the proof in the first place, right? But there are challenges with all four of these things. So when you're building these formal models, what model do you actually want to formalize? Do you want to go all the way to like C or C++ and formalize the language? Or an interpreter or compiler, or do you want to do the CPU semantics, or do you want to even go all the way down into hardware? There's lots of different ways that you could do this. And you've got this other problem where some of the languages or compilers or CPUs just don't even have a formal specification that you can reference. And that makes it hard to obviously write a formal specification of what these things do because you don't know what they do, right? And then when you actually write the model, there's no guarantee that you wrote the model correctly, actually. This is always a problem in formal verification where your model is just a trusted part of your setup. And if you get the model wrong, you get the whole thing wrong, right? So it's very critical that we get that right. And then actually when you're stating the timing constraints, it's actually just hard to write the timing constraints sometimes because you've got these loops that have complex conditions and maybe they have an early return or break or something, and it gets confusing exactly how to write these sometimes. And also the constraints that you're writing should be referencing the inputs to the function when the function started. If you talk about some memory address but only after the function is run, then, and if that expression is somewhere inside of your timing constraint, well now you have to run the code to know how long it would have taken. But that's not useful at all, right? So you have to reference only memory and inputs that were at the beginning of the function. And sometimes it's really hard to show that there's a path to get from the beginning to the end. For writing the proof, you actually have to learn a proof language. If you know me, you know that I talk about Coq all the time. It is a formal verification language. It's very hard to learn. It's very hard to get good at. And that's something that puts a lot of people off of this field. And then even if you know the language, the proofs about this code have to handle these complicated concepts like termination and excitability and non-overlapping. And there's so many things. And then whenever you have to reason about loops, which is extremely frequent, we all write loops, you have to have this non-trivial insight into loop invariance that you really only get by experience. There's no formula for writing these. And finally, when you're employing the machine, can you actually trust that the machine checks your proof? The answer is yes, but don't think about that too hard. That's another 90-minute talk that I can give. So dealing with this first bullet point, I'm going to be talking about the PicNA system, which is something that we've developed here at UTD. There are basically two ways that you can handle verification for some arbitrary language. Either you do top-down formal methods where you basically write code in a proof assistant, and then you extract it to another language that is not a formal system like OCaml or Haskell, and then you can compile that into machine code and you can run it, and you basically keep your proofs at every single step because of some nice properties that the extractors have. But what we're going to be doing is bottom-up formal methods where you have some native machine code already. Who cares what language it came from? Who cares what compiler generated it? Who cares what architecture it's on? We've already got it. It doesn't matter. And what we do is we disassemble it. We lift it into a data structure that our system can interpret and imagine as real code. Put that into our verification language and then write our proofs there. So that turns out to be a really good way to do these things. And not super important for this talk, but I thought I should mention it. So when you are making these formal models, again, so I'm talking about PicNA, which is the system that we use. There's one other system from Virginia Tech that does similar things. I'll be talking about this one. We support most of the major instruction set architectures. x86, AMD, ARM, and RISC-V are the ones that we normally look at. This talk is all going to be RISC-V for reasons that aren't important right now. Our verification engine deals with symbolic interpretation. This is like the core idea of how we write our proofs. We're basically stepping through the code, but we're not actually running it because we don't have any inputs for it. We just treat everything symbolically. And every time you step, you keep track of how the state changes, and you have to write your proofs according to these, symbolic interpretation results and whatnot. And I do want to hammer this in. This is a software verification system, so if you're going to ask me about caching or anything like that, don't, because we don't handle that. That is hardware. We just stick at the ISA level, which does not say anything about how caching works. It's intentionally left up to the manufacturers. All right, so with all of our background out of the way, let's actually talk about timing constraints. What does it even mean to constrain the execution time of a function? Does anyone have a guess? Just curious. What do you think?
To simplify it, like, expedite it?
I mean, but I don't know. I don't know what you mean, but yeah, I don't know. Maybe. I was going to say that we need some arithmetic expression that tells us how many clock cycles it has, right? That's the kind of time constraint we're interested in. Some number, right, that says this is how many clock cycles this code takes. That's good. We like that. And specifically, it has to be parameterized by the inputs. That's what I was talking about with memory at the beginning of the function versus at the end of the function. We want to be able to use this expression to predict how much time this function takes, right? So the only variables that are inside of the timing expression should be inputs to the function or the memory state at the beginning of the function. Really, those are the only two things that we're interested in. And for units, I've been talking a lot about clock cycles. We would like seconds because I think we're humans and not machines, so it'd be nice to have a number of seconds. But the issue is that the relationship between clock cycles and seconds is dependent on physics, like how hot the CPU is and the air pressure and the charge and all these things that we really don't want to even be thinking about. That's that is 10 PhD theses on its own, right? So let's not worry about seconds. Let's just stick with clock cycles. And if you want to do seconds, you can actually, just run experiments to do a rough correlation between clock cycles and seconds. And then the other bonus is that there's a relationship between a certain CPU instruction and how many clock cycles it takes, and it's usually pretty well known, and it's often even documented in the CPU manual. So that's perfect. That's exactly what we want. And then, given our constraint expression, now we got this number. How do we actually relate it to a program? What is the bridge that lets us connect? This is a number of clock cycles. This is a program. This is how many, clock cycles a program takes, right? And the answer is program traces. So a program trace is a history of the CPU. It's just a list of all the old states throughout the function that happen after each instruction gets executed, basically. And these states are also annotated by the address of the instruction that created them. So this is an example of a trace. We've got some state at the beginning. We don't even know what it is. We don't care what it is. It's just some state. It could be anything. And at this point, we haven't run any code, so the total number of cycles is 0, right? And then we run an add instruction. And we say, add together T0 and T1, put it in T5. That add instruction takes 3 cycles according to the CPU manual. So our total cycles is 3 now. And our state has been updated. We see that now we have state prime, which is the old state. But T5 has been updated with a value T0 plus T1, right? Does that make sense? Okay. And then we do another one. We do an OR. It shouldn't be an OR immediate because there's no immediate value there, but whatever. We see that we do the exact same thing again. We update the state. We take state prime, which is our second one, and we update it with S0 gets A0 and A1, right? OR right there. 2 typos, man. But you get the idea. And this can be further unfolded. You can sub in state prime for state RT5 equals that right there, right? So you get this big history of what the CPU has been. And then OR has taken 4 cycles, let's say, so now we've got 7 cycles as the total history of the CPU. And then finally we do a branch instruction. And branches are the bane of our existence as program verifiers. They're very annoying to deal with. We can see that we basically split off into 2 possible cases. One, where we have the same state double prime right here, but now we also have the information that T5 is equal to S0, right? But we also have another case where T5 doesn't equal to S0. And in this last case, we can say that because the branch was taken, it took 5 plus ML minus 1 cycles. I'll get to what that means in a second, but the point is it's different from this other number of cycles. So if the cycles were the same in each branch, maybe this problem would be a lot easier, but branches take different amounts of time depending on if they succeed. So yeah, that's kind of what we got. Is this making sense? Program traces? Any questions yet? Okay. So I've been talking a lot about, the documentation. This is the CPU that I've been working with. And the reason I did it was because it just gives me a table. It says, hey, you want the shift left logical immediate instruction? Well, that takes 3 plus the shift amount divided by 4 plus the shift amount mod 4 number of cycles. Perfect. That's amazing. That's a very simple expression. I can plug that into my verification system and I can write a function that takes in an instruction, and a capital N means it's a binary number because that's what instructions are, right? They're just binary numbers. I do some decoding for it, and I say that if the opcode is 51, then, this is an R type, and I know that, okay, if the func3 is one of these things, then I know that it must be an add instruction, and add instructions take 2 cycles, so I return sum 2. And so the point here is that these 2 things are exactly the same. I just wrote a decoder for RISC-V, and that's why I picked RISC-V, because you can write a decoder in the host language, because RISC-V decoding is super easy. But yeah, you can just write a function that takes in an instruction, spits out a number of cycles. And I don't have it on here, but if there is a branch instruction, right here, we see that if it's taken, it spits out 5 plus ML minus 1 cycles, otherwise 3. ML is the memory latency, which is the number of cycles it takes to grab something out of memory. It's just a variable though, we don't actually care what it is. Okay, so we've set up some good, good machinery to get started on this, and let's stick it all together now. So assuming we have some trace, which is just a list of addresses to instructions and a CPU state, which we call a store. We've got this list of these 2 things. So what can we do? We can just traverse the entire list. Call the, time of instruction function for, each instruction in our trace, and then we can add it to some sum that gets, bubbled through the list. So all this is doing is summing up the value of time of instruction for each item in the trace, right? So ideally, you just run the cycle count of trace thing on a CPU trace, and boom, now we have the number of clock cycles it took, right? But there's an issue here. Data binaries aren't actual code. They're data structures that we kind of imagine as code. And also, even if you had the CPU trace, you wouldn't need to know how many clock cycles it took because you already ran it, right? We're interested in predicting. So how do we actually use this function if we can't run it on a real CPU trace? Does anyone have an idea? It's going to feel obvious once I say it. We're going to write a proof. We're going to write a proof saying that for all possible inputs to some function, the output is some XYZ number of cycles. So we say for all inputs, cycle count of trace T, which is the cycle, which is the trace at the end of the function, it's going to be this expression that we were talking about, the timing expression, right? So let's look at a tiny example. This is a loop in RISC-V, and what it does is, if you look at the top left here, it takes 2 numbers in T1 and T0, and it wants to add them together. How does it do it? It subtracts from the left one and it adds to the right one over and over until eventually one of them is 0 and you stop. And now you know that the other one has the sum in it, right? How many times is that loop? Let's say we're adding X and Y. How many times is the loop going to run? Shout it out.
X minus Y?
Not X minus Y. No, it's going to run X times. If we're decrementing X and we're quitting the loop once X is 0, then our loop is just going to execute X times, always, right? Great, that's important knowledge to know. Also, this is that data structure I was talking about before. It's not code, it's just information, kind of, that we use to symbolically step through. So don't worry about most of this, but this right here is our timing expression for that add loop. And 9 plus ML minus 1 is some setup time. That's the time for the OR I and AND I up there. plus one other thing that's not super important. But the important thing is that we have x in here, that x that I was just talking about. You see that the function inputs, x and y, you see that the total time of this program is some setup time plus x times the time of the loop, which makes a lot of sense, right? It's just the number of times we're in the loop times the length of one loop. Yeah, that's exactly how long this function should take, right? And yeah, that's it. I wrote this proof. It works. Let's pull it up. There we go. We say that our code has this amount of time. We state this theorem stating that add loop satisfies all of its timing invariants, which are these things right here. And then we run this proof. And you don't have to know how it works, because if that QED turns green, then basically the system has said, yeah, you're cool, this works. Let's hope. Let's see if it works. Worked last time I ran it. Lots of green, lots of green. Hang on. Oh, that QED's pink too. It's blue. It's good. It's working. It's thinking. Oh my gosh. Look at that. Green. That means it worked. And a beautiful system. You don't have to trust anything about it, but if it turns green, then you know it's good. And while we're talking about this, let me start. If you think that proof took a long time to run, let's start this one while I begin to talk about it. Okay. Come on. There we go. All right. Okay. So that little add loop example is nice, and it's a good way to introduce people to the idea. But that is not going to get me published anywhere because it's too tiny and it's not real code, right? So looking back at our motivation, can we think of some real-time, real-world code that is security sensitive that we can actually formally time and get a good result that we can publish? Initially, I looked at Autopilot, which is a popular open source autopilot software. It's very, very popular. It's well maintained. But the issue is it's written in C++ and it has a lot of weird object-oriented things going on that I can't really, I can't use that yet. Our system is not super comfortable with vtables and dynamic program jumps. So instead I said, who cares about user space? Let's go to the heart of how these real-time applications work. So let's look at FreeRTOS. This is an operating system that is specifically designed for real-time code. You can customize exactly how the scheduler works so that you can prioritize the super important things. You can make sure they don't run too long. But again, there's not really much in the way of guarantees from FreeRTOS. And this is just a blur from their website that talks about how good it is, I guess. It's really popular, though. It is like the default real-time operating system. It's in the name. So I picked this function, vTaskSwitchContext. I already have the answer up here, but someone in operating systems right now, tell me what you think that does. The answer's on the screen, guys. I know you know it. Someone just shout it out. Context. Yes, it switches the context of the CPU. So your CPU is doing like 1,000 things at the same time, right? But it's only got 4 cores maybe, so it needs to decide how to do the 1,000 things kind of in parallel. Not really, it's going to stop one and run the other, so it looks like it's running in parallel. But so basically what this function is doing is it is saying, yeah, okay, we're going to switch context. I'm going to go look at all the available functions that are ready to be, or processes that are ready to be switched to. Let's decide which one of them has the highest priority, and let's set up everything, and then give it off to the hardware to actually do its thing. Oh yeah, and it's very critical because your CPU is doing context switching so often. Obviously, if there's a timing leak in the context switcher, then all of your timing sensitive code is going to be very dangerously unsecured, right? So if there's a timing leak, then planes crash, reactors melt down, etc. And another thing about it is the control flow for this code is fairly constrained, but still fairly interesting. It has some interesting memory problems to solve. So the TLDR is that this is a real-world example with real security implications, and it provides a compelling yet doable case study for the practicality and utility of this timing system that I've been coming up with. So, in my opinion, that's a pretty great example for a paper. And this is its timing expression. That's it. There's not too much to need here, I think, but you can see that if the scheduler is suspended, then it's only got like 5 cycles plus some change for branching and memory accesses. But if the scheduler is not suspended, it's going to take all this, right? It's going to do some memory reads, it's counting leading zeros for some reason that I still don't know, and 25 cycles, 22, 19, like it's taking much longer, which should make sense. It's a big function. It's doing lots of things, right? And so let's see if that proof has started to work yet. Yeah, it's still going. Oh man, it is chugging. Yeah, so this proof is taking a lot longer because it's really big and my computer's real slow. But I wrote the proof and I promise you that it turns green at the end, so you can just believe me. I did run this earlier today and it took 27 minutes to fully compile. And if you've ever written Koch code before, you know that proofs don't normally take 27 minutes. They take like 1 second maybe. In fact, I'm pretty sure this just is hanging on memsolve right now. Whatever, you get the idea. I just finished this proof yesterday, and I've been working on it for 2 months, so I'm incredibly happy that it finally works. It was a very sleepless weekend for me. Okay. All right, my final example, so I mentioned cryptographic timing attacks at the beginning. So if you've got some cryptographic cipher, and it's got branches or looping in it, right? That cipher can actually be reversed. So, some ciphers can be reversed if the attacker has any kind of intimate knowledge of how long the cipher takes to run. So if they're watching, network traffic, and they know that someone's submitting something to be encrypted, and then the server takes, 5.3789 seconds to return. Oh, they're thinking, it would have taken 5.345 seconds to return if the plaintext had this in it. And then they can figure out what was in the plaintext. It's a really, really cool side channel attack. And yeah, it's just really neat. And thankfully, people have realized this a long time ago. And they started the field of constant time cryptography, which is the idea that you should write a cipher that specifically does not have timing differences. When you take 2 branches, neither of them should have any significant difference in the amount of time that they take to run. Specifically, if one of the timing differences is because of a difference in the plaintext, right? And so this is actually a future/ongoing work for us. We want to verify that an encryption cipher is algorithmically invulnerable to timing attacks. So this is something people bring up a lot. It is algorithmically invulnerable, but maybe your CPU instructions take slightly different amounts of time to finish depending on the cache contents and this and this and this. So maybe that's another way to look at this. But another reason I was interested in RISC-V is because there's an extension to RISC-V, I think called ZK-T, that is specifically designed to replicate all the normal instructions, but their implementations are timing consistent. So no matter what the arguments to the of the instruction are, the instruction always takes the same amount of time. So I've had this idea for a while that if you could pick a cipher that's known to be timing invulnerable, and then write a pick-and-A proof that it's algorithmically invulnerable, and then have a proven timing invulnerable instruction set on a secure CPU, that would be a really, really cool thing. I'm very interested in going down that path. And then how do you actually show invulnerability? Let's imagine that we have this proof for invulnerability in Picnet using all this timing machinery I've shown you. Can anyone think of how you would know it's actually invulnerable to a timing attack?
I mean, is it?
What do you think?
It would just always take the 0 on the time.
That is one possible, but there are other ways something can be timing immune.
Because there's no for loops that are like dynamically sized.
Right, but what would that look like in the timing expression? Because the timing expression is, what is it parameterized over? Yes, perfect answer. If you look in your timing expression and you see no sensitive variables in there, congrats, it is immune to timing because it doesn't take any different number of cycles depending on the sensitive data that you've decided, right? It's completely arbitrary what you decide is sensitive. Do I have? No. Okay, so the cipher that we're looking at is Cha-Cha-20, which is a pretty popular cipher. It's specifically for timing invulnerability. And the loop variable for Cha-Cha-20 is the length of the plain text. So that is the only thing that is leaked out of timing, assuming that there's no bugs in the code. We're working on that. But yeah, so that's the idea, is that if you consider the length of the plain text to be sensitive information, then maybe you shouldn't be using Cha-Cha-20 because that's what it's parameterized over, right? So the TLDR, this whole, question.
The last page. As an example, I know that Flutter has like their constant time modeling. Would that also be like invulnerable? Is it invulnerable? Like they have like a
I mean, I'm aware of the lava lamps. They use them for like random seeds.
yeah. So because lava lamps are constantly changing,
Right.
the code is also constantly changing with it.
The seed, I mean, they're only getting a seed from it though, right? They take the image and they, huh?
That would just be the input.
Right.
Yeah. So I was just saying, is that would that be like an example?
I don't know, is there an algorithm there? If it's just getting a seed, then I don't think there's even a timing attack that can be done with that, right? It's just, there's an algorithm being run. Maybe I don't know. Yeah, that's kind of, maybe there is some timing security issue there, but I think it's out of the scope for this specific approach. We just deal with timing algorithms.
This may be fun offense, but we can talk about this later. But what kind of, like, okay, let's say that the pseudo-random number generator based on Cha-Cha-20 or some other string cipher.
Yeah.
What can you prove about that? Like, can you prove that it's truly pseudo-random or is that possible?
If your pseudo-random number generator, if its correctness is dependent upon the fact that Cha-Cha-20 is invulnerable to timing attacks, or if the security policy for your random number generator is dependent on timing invulnerability, then yes, having a proof of the timing invulnerability of Cha-Cha-20 would help in that case.
Yeah, but the list kernel random there is based on that.
Cool. Any other questions? Okay. So yeah, the TLDR is that we have developed a way to write proofs about the amount of time that machine code takes to run. And there exists, like in the real world, there is real-time code that needs these guarantees to actually ensure the physical safety of these critical systems, right? And they can also show the timing safety of cryptographic ciphers, as we've seen. And another thing that I haven't actually touched on, but the trace properties that we've been writing, the cycle counter trace, that's a trace property. That pattern is a really elegant way to add arbitrary capabilities to this proof system, because our proof system right now has this trusted base of CPU semantics in it. And when we started this project, I was considering, do we need to add like a timing register to the semantics? Something that's like kind of hidden from the user, but is still useful. But no, it turns out that in the user space of Picnet, not messing with the protected area, you can add these trace properties, and I've hypothesized that you can actually combine them. So the last time I gave this talk, people were concerned with specifically cache behavior. They're saying, how does this help if cache behavior can still rat you out for cryptography, or what if cache behavior really, really slows down, balloons the number of cycles that it takes? And the answer is that you can write a trace property that simulates cache. If you're really interested and your CPU has sufficient documentation that you can emulate the cache based on, each instruction that has happened so far, then you can write proofs about cache. And that's really cool. And I never would have imagined that would be one of the results that we found out from this project. So I'm really pleased about that. And I'm excited to find a CPU that has documented cache behavior so that I can add that in.
What do you mean by CPU semantics? And two, wouldn't the proof about like emulating a cache be a pain in the ass, right?
Yeah, so on CPU semantics, we have basically a function that takes in the current state of the CPU and an instruction, and it looks up into a table of what is the CPU supposed to do when this instruction happens. So if we have an add instruction and it's adding R1, R2, R3, or adding R2 and R3, storing an R1, then this function has to say, oh, this is an add instruction. So that means we need to update the store. Destination is R1. Okay, let's add together R2 and R3. Let's put it in there. So semantics just describe how a system evolves given its inputs. So you can, there are semantics for high-level programming languages, Python, Java, etc. They all have semantics, and you need to know the semantics to write a compiler or an interpreter or a symbolic interpreter like what we're doing here. And the second question, yeah, it's a real pain to write these proofs. It was really hard. It took me 2 months. And that's one of the disappointing things about formal verification. It's very difficult, and that's why it's not in the public sphere yet. The average person has never heard the words formal verification before, because it's really, really, really hard, right? So, Tim, you have a question?
So, how do you know the CPU documentation is accurate? How do you make proof of that?
You don't know that it's accurate, and that's part of the trusted computing base. Of course, somebody else can go write a proof that their model of the CPU semantics match the Verilog or the VHDL based on known semantics of Verilog and VHDL. You can connect them that way.
Do you like physical, electronic hardware?
Yeah, here's the thing. Even if you're trusting Verilog or VHDL, it's like, well, what if the compiled circuit, what if the Verilog or VHDL compiler is broken? Okay, well, we've got proofs of those also. But then you ship your Verilog or VHDL off to somebody to actually fab the circuit. And it's like, you get the circuit back. How do I know that that guy didn't mess with my design? Or how do I know that the electrons are aligned properly, or that this film isn't messing with the semantics of the CPU somehow? Like there's 1,000 things that can go wrong, and I honestly think formal verification stops at the fabrication part. There's just so much that you would have to formalize. It's unreal. Hamlin says you would need an army of students to write these proofs, and he's probably right. Yeah, it would be really hard, basically.
What do you think about how, sometimes you hear about how the x86 architecture is so complex that people discover brand new things that were never known before about just weird ways to explain it.
Yeah, that's why I don't like writing proofs about x86, because the semantics are really, really complicated. There's flags everywhere. There's weird branch behavior. Like, oh my gosh, just really, really annoying to write proofs about. So in my entire time working on PICNA, I don't think I've ever touched x86. I stuck to ARM for all last year, and then just this summer I started working in RISC-V. And actually, the reason why I love the RISC-V module so much is because for ARM and x86, we have to rely on Ghidra to lift the code into like P code for us, right? And then we turn the P code into our high-level representation in Coq. But for RISC-V, the disassembly is so simple that you can completely write all of this disassembly code in Coq, and you can just take in a binary number that the disassembler you have on your system spits out. And then now you can load that code directly in. It's so convenient. Very happy. I hope I continue writing RISC-V proofs and never have to touch x86 or ARM ever again. Okay, any other questions? Do I have one more bullet? I don't. I'm out. Let's see if the proof is done.
Let me write on one.
It definitely, okay, wait, let's see.
Little bit done.
No, okay, yeah, it's close. Yeah, QED is, that's the part where it takes about 23 minutes to get through. Hammer, I wrote the hammer attack. I don't know if you can see it. And that one, I just throw it at all of these goals that I have, and it solves a bunch of problems for me. So bang, bang. Cool, all right. Is that everything? Okay, thank you very much. Thanks for coming.